Hi everyone. Today we're going to have a look at conditional probability, and to start with we're looking at example 5. So we've got a table showing the results of 100 people who were surveyed between ages 16 and 29 about their preferred choice when eating at a cafe. So we've got a bit of a table here looking at males and females against vegetarian meals and non-vegetarians. And we're going to select one person at random. We need to work out these four probabilities. So the first one is we're looking at the probability that the person selected is a male and usually eats a vegetarian meal. So male and vegetarian. So male and vegetarian we find is 18. So this is going to be 18. That's our desired event out of the total, which is 100. So we get 18 out of 100, or we can say 0.18. The next one we're looking at is a male given that it's vegetarian. So what's the probability we have a male given that they enjoy vegetarian meals? So the event of the person being male, given that it's vegetarian, since we know that it's vegetarian, we're just looking at this column here. So the given that means it changes from the 100 to just looking at this part here. So really we're comparing the males and females. So it's out of the total, which is now 43, because that's the only column that has vegetarians. And we're after our event, which is the males. So it's 18 out of 43 this time. This one over here, the probability that it's non-vegetarian, given that the person selected is female. So the given that it's female is looking at this row here, and our total is now going to be out of 44, because it's given that we've been selected a female. So it's out of 44, and we're interested in non-vegetarian, so it has to be this 19. So it'll be 19 out of 44. And the last one is what's the probability that we have a vegetarian? So vegetarian, we've got 43. And it's out of our total, which is 100. So 0.43, 43 out of 100. So now we're going to have a look at the conditional probability formula. So we've got probability of A given B is found by finding the probability of A and B dividing by the probability of B. So it is important to note that this really only holds for mutually exclusive events. Okay, so talking about the Venn diagram, it's when we have this intersection in here for A and B. So A given B, A and B is this one over the probability of B, which is obviously that big circle. But for independent events, where we have A and B separated, if we chose B, so A given B, what's the probability that we have A given that we've chosen something from B? Well, it's actually impossible to choose anything from A if we've already chosen from B, because there's no intersection. So when the probability of A and B is equal to 0, there is impossible for A to occur. Okay, so A given B, if the A and B is 0, then we can't get A given B. We can change this up as well, so instead of probability A given B, we can say the probability of B given A. It's the same thing, except so it's the intersection of the two divided by now the probability of A this time. So actually I should have B and A. So it's just the divided by the probability of A. So it's always the dividing by the given part, and it's always the intersection on the top. So that's conditional probability formula. We can also rearrange this as well. So if we multiplied top and bottom by probability of B, okay, they cancel. We get the probability of A and B is the same as the probability of A given, given B, A given B times probability of B. So that's just a rearranged formula there. So just having a look at example 6, we've got the probability of A is 0.6, probability A and B, or sorry, A given B is 0.6125, and probability of B dash or not B is 0.2. We want to calculate the probability of A and B. And if we remember briefly ago, probability A given B is the probability of A and B over the probability of B. Now, we're after this one here, A and B, so we can say probability of A and B is equal to the probability A given B times the probability of B. However, we know what A given B is, but we don't know what probability of B is at this moment. We know what not B is, and so we can use that to work out what the probability of B is by using our complementary events. So probability of B is the same as 1 minus the probability of not B. So 1 minus 0.2, so it's 0.8, 0.8. Okay, so using this formula here, A given B, 0.6125 times probability of B, which we found as 0.8. And if we multiply those together, we will get 0.49. Now the next one, probability B given A, is going to be the probability of B and A over the probability of the given event, which was A. We know what A is. We know what A and B is from our part 1. So 0.49 over 0.6. So 49 over 6. Sorry, 49 over 60. And whatever that is as a decimal. So looking at question 2 or part 2, so we've got 3 girls selecting a ribbon at random out of a bag, one after the other. The bag contains 8 green and 10 red. So we want to find out what the probability, if the first, what the probability of the first girl selecting a green ribbon and then the other 2 selecting a red ribbon. So to start off with, we're going to define G as the event selecting a green ribbon, and R as the event selecting red. So for the first selection, selecting a green, we have 10 green, no, 8, sorry, 8 green and 10 red. So we can select 8 out of 18. Okay, there's 8 out of a total of 18. Once we select that green, there's going to be 7 green left, 10 reds. So when the second person selects the ribbon, we're after a red, given that we've already selected a green. So now, selecting a red, we're going to have 10 out of a total of 17 now, because the first person's already selected a green. So it's 10 out of 17. Then the next one selects another ribbon. So we're finding that there's going to be 7 green and 9 red left. So 16 in total. So now we want to find out what the probability of selecting a red, given that we've chosen a green and a red. So we want a red, which is 9 out of the total, which is now 16. So it's 9 out of 16. So final step is finding the probability of the green and the red and another red. So it's the first one times the second one times third. And if we calculate that, we should get 5 out of 34. So last example, we're looking at example 7. We've got a box of chocolate containing 6 soft center and 4 hard center chocolates. We're choosing one out of the box and will be eaten, and then we'll choose another one afterwards. So let SI, little SI, be the event of a soft center chocolate chosen on the ith selection. So on the first selection, we would have S of 1. On the second would be S of 2, etc. And same thing for H. So H1 would be the first selection, H2 second selection, so forth. So we want to work out what the probability of our second selection being a hard center, given that our first selection was a soft center. So we've got already chosen a soft center, which means that we've got 5 left over. So there'll be 5 soft centers left over, and there's still 4 hard center. So our total is going to be 9. 4 plus 5 equals 9 in total, and we want to work out how many H, so we're going to have 4 out of 9. So there's 5 hard chocolates left over out of a total of 9. So now we want to construct a tree diagram. So we've got our first choice, and we can either choose a soft-centered or hard center. And choosing a soft center is a possible 6 out of a total of 10. And for hard, we've got 4 out of a total of 10. On our second choice, second choice. If we choose a soft center first, we can either choose another one on our second go, or we can choose a hard center on our second go. If we choose a soft center, another soft center, we're going to have 5 now, because we've already chosen a soft center, out of a possible of 9, because we've already chosen one. Which means that there's still 4 out of 9 left over for the hard center. And similar for this one here, if we choose a hard center on our first go and then a soft center, there's going to be 6 soft centers out of 9. But for a hard center, we've got 3 left over out of a possible 9. And just notice that this one, if we added those two up, we get 1. And same thing up here. They have to equal 1 because we have to have the event. It's not all 4 added up to 1, it's just those 2 on those 2 leaves. So that's a tree diagram. So now we just want to have a look at finding the probability that we choose a hard center on our first selection and then a soft center on our second selection. And there's only really one way we can do that, and we just follow the branches. So H1, I'll use a different color. So H1, we have to go this way, and then we want a soft center on the second selection. So we have to go up this way. So there's only one way I can get H1S2, and we get 4 out of 10 for that probability first, and 6 out of 9 for that one. And all we need to do is multiply the branches. So if we do that, we should get 4 out of 15 if we simplify that. And then looking at the probability that we get both either soft centers or both hard centers. So probability of S1 and S2. Okay, selecting a soft and then another soft, and the probability of H1 and H2. So similar to this one before, there's only one way I can do S1, S2. So 6 out of 10 times 5 out of 9. And there's only one way I can get H1, H2. So 4 out of 10 times 3 out of 9. If I work those two out, I just need to, it'll be 30 out of 90 and 12 out of 90. And then final step, I need to add them together because I want either one. So 30 out of 90 plus 12 out of 90 will give me 42 out of 90. Simplified a little bit, 7/15. So that's the probability I either get 2 soft centers or 2 hard centers. So that's all we need for conditional probability for 8.3. Have a go at the questions. Thanks for watching.